everyone. So for some reason I can't just get a little screen of just this man, I can't even speak today. I can't get a little screenshot of just the problem I'm solving here, so you get to see my whole tablet. So sorry about that, but moving on. So looking at this problem here, we're trying to find the speed of a spring launch ball. So we have a spring-loaded toy gun, and it's used to launch a 10-gram plastic ball. Alright, so kind of listing things. We know that the mass here is 0.01 kilograms. Right, so I converted from grams to kilograms here, SI units. The spring, which has a spring constant of 10 Newton over meters, is compressed by 10 centimeters. Alright, so spring compression, we're going to use X to note that. 10 centimeters, that's 0.1 meters. Anyway, the spring is compressed by 10 centimeters as the ball is pushed into the barrel. When a trigger is pulled, the spring is released and shoots the ball back out. What is the ball's speed as it leaves the barrel? Assume that friction is negligible. So this problem here, it'd be easy to predict this to be kind of a free response style problem on the AP exam, where they wouldn't just have this would be kind of one step in the problem, where maybe this now becomes a horizontal launch problem with kinematics. Maybe the problem asks you to find how far the ball falls when it's being launched from the spring. Alright, so where they may not even tell you need to do this mediary step of finding the speed as it leaves the barrel. That's something you have to realize yourself. But I digress. Looking at this problem here, we cannot use kinematics to solve it. Right? Why is that? Right? So looking at our object, let's draw a quick free body diagram while the object is being pushed by the spring. Alright, so here's the ball. Alright, we've got the spring force acting on it, so let's assume that the spring force is going to be pushing rightward on the object, on our ball. Therefore, our object will be accelerating rightwards, its displacement will be rightwards. And we also have force of gravity acting on it, as always. And then we have some sort of, we'll call maybe a normal force upward to have our acceleration be completely horizontal here. Alright, so why can we not use kinematics? So remember that the kinematic equations can only be used when acceleration is constant. We're dealing with the force of a spring here. Remember, the force of a spring has the form kx. Right? Technically speaking, we're dealing with magnitudes here. I digress. The spring force, its value is changing depending on the position of the spring, how much the spring is stretched or compressed. So the spring force is non-constant, which means acceleration is not going to be constant, so we cannot use kinematic equations. So we're going to be forced to use energy principles here to solve the problem, which is fine. I find energy principles to be easier to use. Alright, so we set up a free body diagram. Now let's think about what we're going to call our initial and final situation. Since we're going to be dealing with energy, we want to be thinking along those lines because we are going to be using the work-energy theorem. Work equals change in energy. Well, change in energy is final energy minus initial energy, so we need to pick what we're calling our final and what we're calling our initial. So here it's going to be convenient. Well, we know a lot of information. Well, not actually that much, but we know information about how much the spring is compressed. Alright, so if the spring's compressed, well, we also know that when the spring's fully compressed, its speed is 0. So let's call that our initial situation. So kind of sketching that out. Alright, so maybe this is the barrel of this toy gun. And we have a spring here, and the spring is squished. It's compressed. And then we have our ball here. Alright, so we'll say this is fully compressed. So that's when our x is equal to 0.1 meters. Alright, we also know that our speed here, we'll call this our initial, is equal to 0. Alright. So now we need to think about our final location. Well, since we're trying to find the speed of the ball as it leaves the barrel, well, that's going to be where we're interested in. So here we have the ball leaving the barrel, and now our spring is relaxed. So spring relaxed, meaning it's not stretched nor compressed, and the ball leaves the barrel. and we'll call that VF, and that's a question mark, and I'll circle that to remind myself that's what I'm solving for in this problem. All right, so initial final situation deemed, but we're going to be applying the work energy theorem, which means we need to define our system. It's going to be convenient here, since we're dealing with the spring, to include the spring in our system in addition to whatever object, so our ball. So our system, let's define it to be the spring and ball. We do not need to worry about including Earth in our system here because our object here is not changing height. All right, if our object was changing height, then it'd be convenient to include Earth in our system. Nonetheless, we'll include the spring and the ball. So therefore, internal forces, well, that's going to be any forces of the spring and the ball interacting, which is the spring force here. All right. External forces are going to be this normal force and the force of gravity. All right, because the normal force is caused by the interaction between the ball and the barrel, which the barrel's not in our system. Gravitational force is with the Earth. Earth's not in our system. So they're both external forces. So therefore, when we apply our work energy theorem, work is equal to change in energy. Well, work is done by external forces, so it's the work done by our normal force plus the work done by our gravitational force is equal to our change in energy. All right, so now we need to think about what energies we have to worry about. We always need to worry about change in kinetic energy. And then looking at what we're calling our internal forces, we've got spring force, which means we're going to be using spring potential energy, plus change in spring potential energy. All right, work done by normal force and gravitational force. Well, our ball is moving to the right, it's displacing to the right, and since work is equal to FD cosine theta, where cosine theta is the angle between the force we're analyzing and displacement, well, both the normal force and gravity are perpendicular to that, so they do not do any work. So the work of each of these is 0. So that's nice. That means the way we chose our system, it was an isolated system, and there's no work done by external forces. Right? Yay. And that's going to equal our change in kinetic energy, so that's our final kinetic minus initial kinetic, plus our change in spring potential. So that's our spring potential final energy plus spring potential initial. Maybe kind of annoying subscripts here, but nonetheless, it'll be convenient to figure out what any of these are, if any of these are 0. So looking here, well, we know kinetic energy equals 0 when an object's not moving. Well, in our initial situation, when the spring's fully compressed, our ball is not moving yet. So our initial kinetic energy is 0. Spring potential energy is going to be 0 when the spring is in its relaxed state, when it's not compressed or stretched. That's because spring potential energy has the form 1/2 kx squared, where x is how much it's compressed or stretched. So that means that our final situation, our spring is relaxed, so that is 0. Ooh, I made an error here. Hopefully you guys caught that. I forgot to put it, let me just erase here. It's change in energy is final minus initial. Sorry, I accidentally put a plus sign there. All right, so our expression simplifies. We have 0 is equal to final kinetic energy, so that's 1/2 mvf squared, minus initial spring potential energy, so it's 1/2 kx initial squared. How much the spring is compressed. Always mix up those words. All right, so we have 1/2 kx squared is equal to 1/2 mv squared. So the 1/2s cancel, so that's very convenient. And we're solving for speed here. And just making sure we have enough information to solve this. We know spring constants, we're good there. We know x, and we know m, so we have enough information to solve here. So rearranging, we end up with our final speed is the square root of kx squared divided by m, which when we plug in our values, making sure that we did convert, which we did earlier, we end up with about 3.16 or 3.2 meters per second for the speed of which the ball leaves the barrel. Which then, if we wanted to find how far the object goes, if we knew the height that this is launched from, we could do that using kinematics, or even energy actually. That would probably be simpler. We could use energy to solve for how far the object goes. All right, so hopefully that was helpful.